Let's talk about cryptographic key exchange. The problem is as follows. We have two cryptographic agents whose names are traditionally Alice and Bob. They want to communicate. Alice wants to talk to Bob and Bob wants to talk to Alice. And with secure communications. So to this end, they will try to encrypt their messages, and to do that, they will have to use keys. There are at least two solutions to that. The first one is so-called public key cryptography, which is the subject of another lesson. In public key cryptography, you use an asymmetric scheme with two keys, one for encryption, one for decryption. And the other possibility for Alice and Bob to communicate with a secure key is to use symmetric key cryptography with only one key, both for encryption and decryption. But then you need to agree on a common key, which should be secret, unknown from any other person. And since I'm paranoid, as everybody in security should be, Alice and Bob can't have any influence on the final key. I can't rig the key. If I'm Alice, for example, I can't rig the key so that the final key we will share would have some properties that I would desire in advance. These two problems were actually solved in 1978 by Whitfield Diffie and Martin-Hellman. And we should also mention Ralph Merkle, who was also one of the co-inventors of these techniques. And we shall concentrate on the problem, how can we distribute, but in fact we don't want Alice and Bob to learn the key from outside, how can we create a common key? To this end, we shall use the notion of a cyclic group. Cyclic group is a group which we write with multiplicative notation in a unit, which has some properties that I will illustrate presently. The typical example of a multiplicative cyclic group is the group Z over PZ star of all non-zero integers mod p with multiplication mod p. So for example, in this group, for p equals 11, 4 times 7 would be the remainder of 28 by division by 11, which is 28 minus 22 equals 6. In this group, you have elements which I'm going to call G as generators, such as we can take G equals 2, for example, such that if you write G, G squared, G cubed, G4, G5, and so on, you will enumerate all the values of the group. So we can find every element in here until we find the unit of the group. So we find all the elements, 1, 2, 3, 4, 5, etc., until we reach 10. And this is the definition of a cyclic group, essentially. We shall see it more clearly later. A cyclic group is by definition a group in which there is a generator, meaning an element G, such that you can reach any element of the group by enumerating the powers of G. And a picture being worth 1,000 words, let's draw a cycle. You can imagine that you start from the unit 1, and that multiplying by an element, let's say by 2, the generator here, you will get the element obtained by rotating the first element by a certain angle. If you continue multiplying, you'll get 4, 8, 5, etc. And you will eventually enumerate all the elements of the group, which are the marked points on the circle. A characteristic feature of generators, as you can see from the example, is that the first exponent where G to this exponent gives you 1, which is called the order of the element. So here the order of the element 2 is 10. Well, it so happens that the order of a generator is exactly p minus 1. So having a generator is also equivalent, in fact, to the fact that the order of G is p minus 1. That is, the first power of G that gives you 1 is p minus 1. Now at last we can describe Diffie-Hellman's protocol. It's a protocol whereby Alice and Bob will exchange two messages, either in sequence or in parallel in any order. It doesn't matter. They first agree on a generator G, and then A will create at random a new element mod p minus 1 and send G to the A mod p to B on a public communication channel. B will do the symmetric thing, create a new exponent B and send G to the B mod P. So now G to the A and G to the B can be deemed to be public in the sense that anybody who will spy on the communications channel will be able to learn these values. But A and B are secret, since A and B will hide these values and keep them for themselves. Despite this secrecy, both A and B can compute the common key, which is going to be G to the AB mod P. For example, Elise can compute it by taking the public value G to the B, putting it to the A, which is secret, but Elise knows A, and this is equal to G to the AB mod P. And symmetrically, B can compute exactly the same value by taking the public value G to the A, taking it to the exponent B, which it knows, and this again gives you G to the AB mod P. The security of this scheme is based on an algorithmic problem called the discrete logarithm, log base G. And what is this beast? Well, the fact that G is a generator means that there's a map which maps every integer to its power mod P, and it so happens that this is a map from the additive group Z over P minus 1Z to the multiplicative group Z over PZ star times. That G is a generator means that this is an isomorphism of groups. In particular, it has an inverse, which is called the discrete logarithm base G, in which, by definition, finds the n, given an element of the rightmost group, G to the n, it finds you back the exponent n. It turns out that computing this is hard. Let's see what the connection is with Diffie-Hellman. Well, the first thing is, if that were not hard, so if log G was easy to compute, then Diffie-Hellman would be broken, meaning the following. So assume an intruder, an adversary, Charlie, spying on the communication channels. And so we'll be able to learn G to the A and G to the B. But if the logarithm was easy to compute, it would be able to compute A, for example, which is just the logarithm of G to the A. And then to compute the key, which is G to the B, which is public, to the A, which is it has just computed. So if the discrete logarithm was easy to compute, it would be easy for an adversary to get the common key. That is not a complete security argument. We would actually want to prove, question, whether the converse direction holds. That is, if log G is hard to compute, is DH Diffie-Hellman safe? It's generally believed so, and in particular Victor Schupp provided an argument that log G is as hard to compute, as Diffie-Hellman is hard to break in the so-called generic model, which I won't delve into because it's really too technical. As a conclusion, I would like to mention 2 points. The first one is, today, DH is considered safe for a variety of reasons, but in particular the fact that no one is actually able to break it in practical cases. The second thing is that you may replace Z over PZ star by other cyclic groups. In particular, one may well consider cyclic subgroups of so-called elliptic curves, which have been very popular in the last decade.